So in the last video, we talked about the heat of reaction. But how do you measure the heat of reaction? You do that through something called calorimetry. The heat flow is measured using calorimetry. And actually, we use a very sophisticated piece of equipment known as a styrofoam cup to do this. And it's referred to as a coffee cup calorimeter. Basically, we run the reaction in the styrofoam cup, measure the temperature change, and we can use that information to calculate how much heat was released or absorbed. Okay, in order to do that, we need to know something about a quantity called specific heat. Okay, specific heat, which is abbreviated CP, is the amount of heat that's required to raise 1 gram of water 1 degree Celsius. So, on this chart for aluminum, the amount of heat required to raise 1 gram of aluminum 1 degree Celsius is 0.902 joules. So you can see in this chart that some things metals typically have low specific heats. And you'll notice that water has a very high specific heat. So you're going to be dealing with water quite a bit because most reactions happen in aqueous solution, especially when we use coffee cup calorimeters. You notice the specific heat of water is 4.18 joules per gram per degree Celsius. That is extremely high. So it takes a lot more heat to raise the temperature of 1 gram of water 1 degree Celsius than 1 gram of any metal 1 degree Celsius. And that is actually the high specific heat of water helps create life on Earth because the oceans act as a giant heat regulator. So it takes a lot of heat to heat the oceans up, and it takes a long time for the heat to be radiated off. So this slowness in the amount of time it takes for the heat to be absorbed or released regulates the temperature of the Earth. So we don't have the wild temperature swings that you see on other planets that do not have water on them. So that's a very important unit that we're going to be using in our calorimetry calculations. So, as it turns out, when we carry out a reaction in a calorimeter, that's under constant pressure. So, the heat evolved, the Q of the reaction, is the same as the delta H of the reaction. So, we can use the same thing that we use to figure out the Q of the reaction, we can use to figure out the delta H for the reaction. So, the Q of the reaction is equal to the mass of the reaction times the specific heat times the change in temperature. And the change in temperature is always the final temperature minus the initial temperature. Final minus initial. So if we think about this, if I have an exothermic reaction, T final minus T initial is going to be a positive number. So when Q reaction is positive, that is exothermic. If I have an exothermic reaction, delta H is negative. So when we use Q equals mass times Cp times delta T, you have to realize that Q and delta H have the same magnitude but opposite signs because Q is measuring the surroundings because the thermometer is part of the surroundings. Delta H is associated with the system. It's associated with the actual chemicals that are reactive. So as long as you keep that in mind, you can use this equation to calculate delta H. So let's take a look at an example problem using calorimetry. Okay, so we have 100 mils of 1 molar NaOH and 100 mils of 1 molar HCl mixing. Both of them started at 24.6 degrees Celsius, so that's your initial temperature. After the reaction, the final temperature is 31.3 degrees Celsius. Assuming that all the solutions have a density of 1 gram per cubic centimeter, which is the density of water, which means that the volume of water, or the volume of solution, is equal to the mass of the solution. That's what that density tells me. And the specific heat capacity, here we go, 4.184, the same as water. We want to calculate the enthalpy change for the neutralization reaction. And we're assuming no heat is lost. So Q for the reaction is equal to mass times specific heat times delta T. So in this case, the mass, what is actually sitting in that cup, is a total of 200 milliliters of water, of solution, not just water, but of solution. We're assuming the solution is 1 gram per cubic centimeter. So if I have 200 milliliters of solution, I have 200 grams of solution in that cup when they are mixed. The specific heat is 4.184. And then to calculate delta T, you subtract 31.3 minus 24.6, and you get 6.7 degrees Celsius. So to calculate the Q for the reaction, you simply multiply those three numbers together, and you get 5,600 joules to two significant figures, because that subtraction, there's only two significant figures, which would be the same thing as 5.6 kilojoules. That's the Q for the reaction. Now, since this Q is positive, that means that delta H for the neutralization reaction is negative 5.6 kilojoules.